Yes. So seminar 5. And the first one is asking you to check if it's homogeneous. Okay. And I'll write the functions first, and then you'll see what I'm doing. Okay. So I guess the only reason you would memorize homogeneous is because it's a I would say international math property in the sense that homogeneous applies to vectors, matrices, basically everything, any transformation, any function. So that's one reason to memorize it. If you are actually going to study math or something related to it, you're not going to run away with homogeneous. There are a lot of properties about it. But in your case, what does homogeneous mean? It just means that if you apply the function to t of x, t of y, you just get proportionally more stuff. Well, this is what homogeneous means. You can think about it as I have a cheese factory, I need milk and people. If I just double all the inputs, I'm going to get twice as much cheese. Okay. If I put 2 times more milk and 2 times more people into my production thing, then I'm going to get 2 times more cheese. That's basically the whole idea of homogeneous. Okay. And not all production things have this properties, but that's kind of how I think about it. Okay. Now let's do the first one. The procedure is quite simple. You just put tx, ty, and see what you get. There's not much I can say here. So I plug in tx and ty instead of my x and y up top, and I get tx plus ty, tx everything squared, plus ty everything squared. And I would ideally want to bring it to something of that shape. Okay? So let's see if we can do something. We get a t up, x plus y, we get a t squared below, x squared plus y squared. This simplifies and I get 1t x plus y, x squared plus y squared. And now you need to observe that this x plus y, this thing is just f of x, y. So just rewriting what I did was this is just f tx ty is equal to 1 over t, or t to the minus 1 if you want to make it like look exactly like the definition, times this. So this by definition is homogeneous degree minus 1. You know, it can be negative. If you want me to give an example, you can just take this f as being my health. Okay, this is just my health, and it depends on how much x is how much chocolate, and y is how much pizza I eat. Okay, if I eat twice as much, if I eat double my quantity of chocolate and pizza, I'm gonna be worse off. I'm not gonna be healthy. Okay, that's how you can think about it. Obviously, there are more I don't know, elevated examples, but I think this is the easiest to come to mind, and I hope it makes sense to it. Okay, now this b is f of x, y is equal to 0. This is a little bit tricky in the sense that you gotta wrap your head around it. What's the definition? Definition is f of tx, ty is equal to tn f of xy. Okay, this is the definition of homogeneous, but you know that the function is 0 everywhere. So it means this is 0, it means this is 0. So you have 0 is equal to t times t to the power of n times 0, which is true for any t and any n. Right, 0 times 0 is equal to 0. So at this point, the idea is that this function is homogeneous of any degree n. Okay. Again, the logic I used is if f of xy is equal to 0 for all values of x and y, then in particular, if I write a definition of being homogeneous of degree n, in particular means that this function is going to be 0 just because it's 0 everywhere, and this one as well. So I get 0 is equal to t times n, t to the power of n times 0, which is going to be 0, right? So at this point, I can say that it's homogeneous of any degree n. Now, I've read some of the lecture notes, and I'm a little bit confused myself in the sense that he uses homogeneous of any degree n quite often. But what he means is you fix a degree n, but that n can be anything, okay? So when in his notes, he basically says something like, this property, you know, dot, 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 I don't know, this property, you don't need to write, you probably already wrote in your lecture notes, holds for homogeneous of any degree n. Okay, I'm pretty sure he wrote that somewhere. So what he means is that this property holds for any function that is homogeneous of a degree, okay, of a degree n, where that n can be anything. So he basically says that property holds for homogeneous of degree 1 or 2 or 100, okay, but not all at the same time. That was a little bit confusing. Well, what I'm writing here, this is, I think, what I've used in these natural writing. I'm just saying that according to my definition up top, this function is homogeneous of degree 1, 2, 3, 4, 5. It's homogeneous of any degree there. Okay, I'm just saying that homogeneous of any degree n. So in particular, homogeneous of degree 1, 2, dot, 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 100, 200, 127, dot, dot, dot. Okay, it's homogeneous of any degree. I can put n be whatever there. I just wanted to clarify this. When he means in class, he's referring to just fix an n, and that n can be whatever. I'm saying here that that this function f of xy is equal to 0 is homogeneous of all values. Okay. Hope that makes sense. And then point C, that's again f of xy is equal to xy to the third plus x to the third. I'm just gonna slap a t here, and I get tx times ty, everything to the third, plus tx, everything to the third. Doing some simple computation here, I'm gonna get one t from here, 3 t's from here, so I get t to the fourth, x, y to the third, plus t to the third, x to the third, and I can factor out the t to the third, and I get t, x, y to the third, plus x to the third. Now, is this homogeneous? No, I would have liked to have an f of x, y here, but that's just not true, because I have this t here, which makes it different than the initial function. So is it homogeneous? No. Okay. Cool. Now let's do the one that was, I guess, a little bit more confusing with the Hickson demand, etc. Again, a little bit weird on the notation, which I think was a problem for a lot of you. So he says, let me copy it fast. It says HIP U is equal to HI P1, P2. Yeah, that's 0. And then show. Is there a B? Why is there an A and no B? I just noticed. Okay. All right. So the problem here that I don't think it was necessary is this I here. Okay. I don't really understand the point of this I. And this was a problem for a lot of you guys because when you wrote the function here, when you wrote this sum, if you use this I notation here, then some of you notice that, hey, I have I here and I have I here. And at that point, nothing is going to get solved. So my suggestion is to either drop the I in this case because it just doesn't matter. It's the same I for everyone. It's not like this one. If I change this to J, this is going to become J, but this still stays I, if it makes sense. I don't know. That's why I'm saying the notation was a little bit confusing. And I don't personally see the idea of HI, maybe because he wanted to make it shorthand for Hixian. But just keep in mind that this I just goes for everyone. Okay, it doesn't matter. It's just how your function was defined. Anyway, the Euler theorem. The Euler theorem applies to homogeneous functions of degree n, where n can be any number. And if you just have your function f of x1, x2, xn, then it basically says that if you take the derivative of each of the, the function with respect to each of the inputs, so x1, and you multiply it by x1, this, and then you add them all up together. Dot plus dot dot dot. You are going to get f, no derivative, no nothing, times n. Okay, this is what this Euler theorem says. What's the interpretation of it? I don't really know exactly how to explain it. We can explain something in terms of being that it's homogeneous, it just increases kind of directly in each of them. And then when you multiply with x1, you just get approximately 1f. But again, that's something way beyond the scope of the exercise or the lecture. Okay, it's just an Euler theorem. It's just something to keep in mind. There might be trick moments where you can use it. Really niche though, but a theorem is a theorem. Maybe it comes in handy someday. Let's see how we use it. We're gonna use it here though. Now, for the sake of not writing 20 pages, I'm just gonna use the sum notation. I hope everyone is comfortable with that. Otherwise, just let me know. So this whole thing can be just written as sum derivative of f with respect to xi times xi is equal to f times n. Okay, I just rewrote everything shorthand for it. Okay, now one thing that I have to comment here is I partially, notation-wise, let's just put here, let's say it's homogeneous of degree A, then it's just A here. Okay, it's times the homogeneous at the end. I don't want to be any confusion with the n here. That's what I changed. This n is the counter, this A is the homogeneous. You have A here. I just realized it might be a little bit confusing, so just wanted to make sure. Okay. So what's the elasticity formula? The elasticity of Pj, okay, let's do P1 first. Of P1, with respect to Hi, we're gonna keep kind of this notation because I don't know why, but we're gonna keep it. This is gonna be equal to P1 over HIPU times the derivative of this HI over, of P1. Okay, just the formula of elasticity. Hopefully I didn't get it wrong. I usually get it 19 out of 20 times I get it wrong. So hopefully the sum is correct. And now what we do from here is we're asked to compute the sum of all of these. So I'll write it up. I'll write all of them and then I'll move to the sum. So it's this HI P1 plus, the same thing, but for P2. And really, really important, this is where the confusion came in. This thing is the same as this one. Okay? It's the same function. There's no derivative, there's no nothing. But these are the same. Does everyone get why they're the same, or do I need to explain it? All right, what's the formula of elasticity? So the formula of elasticity, let's say elasticity of x, f of x. This is just equal to x over f of x times derivative of f of x, derivative of f with respect to x. I can put an x here, it doesn't matter. Okay? So basically the whole idea is that this hi is the same for all of them. It's the same function for all of them. Okay? That is the same for all P1, P2, Pn, it's the same. So continuing my multiplication here, derivative of hi with respect to P2 plus ... plus Pn over hi Pu. Again, this same thing as before. Derivative of hi Pn. Okay. Now, let's write it as a sum, but let's be really, really careful. Okay, we're gonna write this whole thing as a sum, so we can see things. Sorry. So let's write this as a sum. I'm gonna write sum from j equals 1 of pj. This is, and now you see why I chose this j instead of the I. I just didn't want to be any confusion with this thing. If I put I here, it would mean that this hi would be different for every value of I. But I just chose to choose this j just to emphasize that this is the same for all. Again, that's the key. If you see that this is the same for all, then there's nothing happening. dhi dpj. Okay? And this is my sum right now. Everyone understood what I'm doing with the sum, how I wrote it, procedure-wise, mostly? Okay, now, the trick with sums, why is it so nice to write like this, is if you have something that is the same for all and does not depend on this j, you can just pull it out of the sum. So what do I mean by this? Is I'm just gonna take this out. 1 HIPU. Okay? This thing doesn't depend on j, it's the same for all. So I just pull it out. And I get sum j equals 1 to n of pj, derivative of hi, derivative of pj. Okay? I don't do much up to this point. But the problem is over. Because if you just look here at Euler's theorem, you kind of get the same exact thing. But let me convince you guys. So this is what I got. I'm stuck. This is what I got from the elasticity. I don't know how to continue. I can't do anything. So let's just apply Euler theorem to our function h of I. Okay, hi is P1, P2, Pn, U. Okay, cool. So let's just see our function right here. I have to do, just copying the thing, applying the formula. I have sum, again, I'll use J from 1 to n of derivative of this hi with respect to xj, which in my case is just p1, p2, so that's pj, times pj, okay? Obviously, the x's here, the x's in the general case are just the p's in my case. What is this equal to? It equals to hi of p1u times the degree of homogeneity of H, which the problem tells you it's homogeneous of degree 0. Okay? So this, because H is homogeneous degree 0. The problem tells you that. Okay? Does everyone understand how I applied it? I literally just applied the Euler thing. 0 times whatever gives me 0. So let's see where we're at. I have that the elasticity thing, the sum of all the elasticities. Yeah, this one. The sum, again, I'll be a little bit careful here. Elasticity of Pj, Hi, Pu is equal to, we just showed it's equal to this, Hi, Pu times sum Pj, derivative of Hi, derivative of Pj, J from 1 to n. Okay, this is where I got stuck. And then I know from Euler theorem. By the way, this Euler guy has a lot of theorems. So if you're stuck, you can just say, oh, it's true because of Euler theorem. He probably has a theorem about that. Okay, this is what I got from Euler's theorem. Now, do we see how we can continue now after I apply Euler's theorem? Do I have like a way of continuing my work here? That's the idea. And here you need to struggle a little bit and look at your equations and notice that this sum over here is the same as this sum over here. Okay, that's the whole idea. The sums are the same. So because they're the same, I can just say that the sum of elasticity and elasticities Pj, Hi, Pu is equal to 1, this Hi, Pu thing, times 0. I mean, yeah, times 0 because this is 0, which is just 0. All right, and that's how I ended my problem. Again, it was just a direct application of it. To keep in mind from here, it's just, I assume the elasticity formula and maybe Euler. Again, maybe you're gonna use it in some case. I have no idea. I can't tell. There are problems that could be solved with Euler's theorem, and I could probably create some, but I'm just gonna leave it at that for now. Let's see what's next. I think next is the problem that I didn't like and it was confusing to everyone. And it was just let me see what time is it. Let's see if we can do it. Yeah, I'll rather just let's do a little bit of limits since this one is something special. Let me look in the stumble group if there's any problem that anyone might want me to do specifically. But I don't remember being anything extremely specific here that was good. Just gonna refresh them to everyone. Just have a raise of hand if you want me to solve anything from the stumble group, if it's gonna download, yes. So again, this is homogeneous. I'll actually want to do homothetic, okay? I'll actually do this one. To basically show you the homothetic thing. And then we're gonna move on to limits. So problem 2 from there's no homothetic, so let's do that. Stumble. I think I misspelled it. Yeah. We'll leave it at that. Okay, so you take for granted that f of xy is equal to xy is homogeneous of degree 2. That the question is wrong. It's homogeneous of degree 2, of course. It doesn't matter, but just to keep in mind, yes, you're not crazy. It's homogeneous of degree 2. G of x y is equal to log of x plus log of y. G of xy is equal to e xy. Okay. This is the problem. So and they're asking if these functions are homothetic. Now, what does homothetic mean? Homothetic means that you can write your f function as g of, okay, let's stick to the notation. I think it's been remembered. You can write your g function as h of f of x. If you can write it like this, where this thing, f, is homogeneous, doesn't matter the degree, just matters it's homogeneous, and this is either strictly increasing or strictly decreasing, then you have G is homothetic. Okay? This is the formal definition I think you gave in class. I'm just putting it out there. Yes, now homothetic, what it means that you had the whole drawing with like these are your ISO costs, and basically you're just scaling your results. But I think it just did that, so I really just remember the formula because it's we're gonna use it, that's why. So let's look in point A. We have this g of x of y is equal to log of x plus log of y. Now you got to keep in mind, this is the definition, and there's no other criteria that you have learned in this class that tells you if something is homothetic or not. So you have to get to something that looks like this. Okay, that is the way you should think. I haven't learned anything in this class. That's a strong statement. I haven't learned anything in this class about proving homothetic outside of the definition, so I need to bring it to the definition. Okay, that should be your logic. And you stare a little bit and you're like, okay, what is log of a plus b? That's just log of x, y. And then you remember that, hey, f of x, y is equal to xy. Same thing. So this is just ln of f of xy. Okay? So if I define my function, so this is my f. If I define my h of z is just equal to ln of z, I can just write this g of xy as h of f of xy. Or even simpler, if you don't want to write this, you can just say, okay, ln strictly increasing. This is homogeneous. Degree 2, if you want, but doesn't matter. Okay, at this point, according to the definition, G is homothetic. Make sense? Again, you all know the definition. The whole idea is to bring it to the f function. So I brought it to the f function using the log rule. And then I just said, okay, this is just ln of f of xy, which is, I know ln is strictly increasing. This is homogeneous. So I am in my condition of, in my definition of homostaticity. Okay. If there are no questions, let's do problem B. As you can tell, it's probably the same. B is just G of xy is equal to E of xy. Again, you notice this is an F, so it's just E to the power of x of f of xy. And you can just say this is the exponential of f of xy. And again, same logic, exponential, strictly increasing. This thing, homogeneous, by definition, homothetic. I know it's pretty easy. I just wanted to bring basically show you how to prove homotheticity. If you were in a more complicated setting, you probably would need to do more, but this is enough for now. Okay, I think this was the last problem I wanted to touch from the stumble group, unless there's some special requirements. Yes. On this one or the. Okay. Yeah. Oh, A. Okay. So this problem number 4, is the exact same idea as you had in the. Okay, sorry. 1 second. Then of x plus y squared. X, y. Show that these points. X plus y is equal to 0. Okay. Cool. So, this problem is the same idea as you had in your assignment, your first assignment. Remember that xy thing? I don't know, xy minus, I think it was 5 minus xy to the power of a plus 1, something like that. Do you guys remember that problem on your previous assignment? I think it was problem number 2. Remember when I kept making the claim that this function does not care about x or y, it just cares about their product? Okay? If you look at this minimizing function, it only cares about x plus y. It doesn't care about x. It only cares about x plus y. So if I take derivative of this, I take derivative of x plus y squared with respect to x, and then I take derivative of x plus y squared with respect to y, and I get 0, 0. And what's the derivative? This is sometimes troublesome for me. This is 2x plus y. I hope I didn't mess it up. Is equal to 0. 2x plus y is equal to 0. So same equation, x plus y is equal to 0. And this is one thing that I wanted to emphasize a lot in the previous homework, that why was it okay to just leave xy was equal to the ugly function? Why is it okay to just leave x plus y is equal to 0 in this case? The reason is that this function, although it minimizes over the choice of x and y, it doesn't care about their particular value. It just cares about the sum, the value of the sum. For example, if I had another x here, the situation would be completely different. Okay, because the function would care what x is in particular. Since I don't have this, it only cares about the sum of x plus y. So what do I mean by this is if x is 5, I can use this to find a corresponding y value that is going to minimize that function. Okay, so I can't fix anything. This is what I have, and it's called 1 degree of freedom. I think you learned that in your first lecture or something. Did you not? No. Okay. Okay. Maybe you're gonna learn linear algebra, although they kind of use that. But we'll take it as it comes. So again, the logic is that you're minimizing over their sum. So the only important thing you're interested in is their sum. The values I can just write minimize over z squared. You see what I mean? Like this would give me the result z is equal to 0. It's the same as for xy. It doesn't matter. I can just put minimize over. I can just write it minimize. I can put as many variables if I want, x, y, z, x plus y plus z squared. They are intrinsically the only one value. Okay, they're just the sum. It doesn't, their particular values don't matter, just what they add up to. Does that make sense? Does that answer your question? So show that all points such that x and y are stationary points. Well, again, I would say we got this. This is the condition for stationary points, and it holds because we're minimizing over x plus y squared, so only the sum counts. That would be my argument for this. Okay. Now for the next one, check the second order conditions. I would just take derivatives. I assume that's fine. Okay, awesome. What's the time? Should we do a break? Let's do a break now early. So I don't want and then we can do the limit part more from top to bottom. So let's take like a 10-minute break now. So is to basically just give you some basics about limits, and then we're gonna attempt to solve this beautiful limit right there. And yeah, that's kind of the plan. If you have any other ideas or suggestions or wishes, just let me know. But limits, okay? So first of all, I will translate the formal definition into the simplest definition I can imagine. So, and it's exactly the same, just I'm going to say it with words also instead of mathematical formulas. When you say that the limit of when x goes to infinity is of, I don't know, f of x is equal to some value c. Okay, let's say it's equal to some value c, where c is a constant. Okay, this is a constant. This x goes to infinity. Okay, so the formal definition translated just says if I take x bigger and bigger, I am going to get very close to c. I mean, f of x is gonna get very close to c. Okay, f of x is going to get very close to c. But this is literally the formal definition. It's just not the, written in a simpler language. So again, when I have limit of x going to infinity of f of x is equal to c, it means that if I take x bigger and bigger, f of x is going to get very close to c. Just a small addition, as close as you want. What does this mean? It means that if you want it to be in closer than 1, I can make it. I'll just take a bigger x. If you wanted to make it closer to, in the range of 0, 0, 1, I can do that as well. I will just take an x even bigger. Okay, does this definition make sense in simple words? If I just take x bigger and bigger, I will get very close to that c. Now, when you have limit of x going to infinity is equal to infinity, it just means if, again, the same thing. If I take x bigger and bigger, f of x is growing bigger and bigger. And in particular, I can make it bigger than any number you want. Okay, does this make sense? And like when you're saying that something goes to infinity, it just means that if if you were saying that limit of f of x goes to infinity, it just says that it just means that if I take some x 1 million, I can make this f of x bigger than whatever value you give me. Okay, this is what it means by infinity. So if you want to just take an example to see exactly what I mean by this, let's have limit of f of x squared when x goes to infinity. Why is this infinity? Well, because according to my extremely formal and nicely phrased definition, whatever number you give me, I can make x squared go bigger than that. Like for example, you give me no, you're just fighting me on this and saying, okay, no, I'm saying x squared is not going, this limit is not going to infinity because you can't make x squared bigger than 124 something 5 8. I don't know, 7 here. I have no idea. And at that point, I'm just going to give the number, I'm just going to give x the value square root of this plus 1. Okay? And so I'm going to make my x squared bigger than that. That is the definition of when something goes to infinity. It just grows bigger than anything you can give me. It doesn't have a maximum. Okay, that is the definition of going to infinity. And when it goes to a constant, let me give an example if I can give you something of a constant. Yes, I can. X goes to infinity of x plus 1 goes to 1. Okay, I don't want to do 0 because that's too simple. There, I'm saying this goes to 1. Again, checking it in the back of my head. If I take x bigger and bigger, it means that I'm going to get very close to 1. That is the definition, as close as you want. Let's say you're saying no, you're wrong. It just goes to infinity, or it stops to, I don't know, it stops at 0.5. I can just take, I don't know, if you see, I can just take 1 million, I don't know, let's do 10,000. 10,001. If I just have 1 minus this thing, I'm going to get 1 over 10,000. Okay, if you want me to get even closer to 1, I can put a bigger x there. I can just get as close as you want to that 1. Okay, that is what the limit means, that I can get very, very close to it. Now, this thing that I showed you is not, you don't need to write anything like this on the exam. Okay, it's just a matter for you to understand what a limit is. It just means that you can get as close as you want to it when it's a constant, and when something goes to infinity, it just grows bigger than anything you ever want. Okay. Now, given that you can just take any numbers you want, I hope that, if we use this definition, we can agree on some extremely definite limits, which, you need to build intuition for it. But unfortunately, I noticed that some of you are memorizing it, which shouldn't really happen because I don't know, the brain, you have so much to learn, and memorizing like some limits like 0 over infinity or 0 over constant is not something you should do. Okay. So let's just look at the simple ones. When I mean limit when x goes to infinity of a constant over x. Where does this go? And I think I asked the student this, and for that moment, just look through the notebook, checked a bunch of stuff, asked a friend, called the phone, called someone, asked my mama, and then she was like, oh yeah, I don't know. And the problem is you can memorize this. Like I can write you all the rules if you want, like 0 over infinity, etc., where they go. But that's, if you don't understand it, you're not going to memorize it. And memorizing this is, you have so much in this class already. I don't think you need this. So let's think about this. Where is this going? And the idea is that now we use the logic with very big, very small. This is fixed. I don't know, put a number here if you don't like to see. This can get very big. As big as you want. That's why it goes to infinity. So when you have something and you divide it into 1 million pieces and then divide it even every piece in 1 million again, et cetera, et cetera. We get something very, very small. So that's why this is 0. Okay? Why is this 0? Again, if you think about the logic, because whatever x I put, whatever c you give me, I can just choose an x that I'm going to be as close as you want to 0. If this is my axis, this is 0, and you say, okay, I want you to give me an x such that you're in this interval. You're in like the minus on this side. You're in the 0.01 margin. I'm gonna be like, sure. X is equal to c times 1 million. Okay, 1,000 I put there. So I can get closer. I can be in this interval. Then, if you want, I can be in this interval. Then, if you want, I can be here. I can be here. I hope you get what I'm saying. I'm just getting closer and closer. I'm getting as close as you want to that 0. So that's why the limit is equal to that thing. Does that make sense? Because that's like the idea. So again, maybe if I just draw this idea again. This is your OX axis, okay? And this is 0. And let's take an example. Let's put C is equal to 2. And let's start at x equals 1. Okay, this is my 2/1. Now you're saying, okay, I don't believe you, this is 0. Look, we're starting really far apart. I'm saying you can't get in this interval of 0. You just can't get closer to 0 than that. And at that point, what I do is let's say this is like a half, I don't know, let's say this is 1. I just take something bigger. I just take x is equal to 5. Okay, that's going to be 2/5. I'm going to be right here. This is my 2/5. So I'm inside this first interval. Then you want me to get even closer. You're daring me to go in this interval. Sure, I'll just pick a bigger number. I'll get 2/100. Then you want me to get even closer. I need colors for this, but I hope it kind of makes sense. The idea is that this interval is just shrinking until it's just 0. Like, I started here, now I'm moving here, and I'm just moving closer and closer to this 0. Until basically there's only that point 0 there. That's what the limit means. It means I'm just getting as close as you want to it. Anyway, let's think about the formula. So, as I said, limit of any constant over x when x goes to infinity is 0. Now, limit when x goes to 0 of any constant over x is equal to, you think about it, you have something, a c, and which is just a constant, and you have x going to 0. So it means you just take any number that's as close as you want to 0. Again, the whole interval thing, as close as you want. But, you can think of it in terms of just comparing them. C is a number, it doesn't matter. It can be small, but it's just a number. And X is the smallest thing you can imagine. If I divide your sandwich into the smallest thing you can imagine, how many pieces of your sandwich I'm going to get? I'm going to get an infinite amount. Okay? I could technically feed the whole world with your sandwich if I split it small enough. Okay, so that's the idea. This, very small. This, just some size. So again, think of it, I have something, you have your cake, and you're splitting it into the smallest pieces you've ever imagined. How many pieces you're going to get? You're going to get a lot of pieces. Okay, so I'm saying this goes to infinity. Now, the logic again that I used up to this point makes sense again, because I can just choose my x close to 0 and take these values 0.1, 0.01, 0.0001. And I'm gonna get this is my x, then my c of x is going to be 10c, 100c, 1000c. Etc. etc. As you can see, it just goes to infinity. All right, I should have made a claim, but we're going to assume that c is positive, just so I don't get minus infinity. Okay, what else? What are limits are you interested in finding out? I don't know. What is x goes to 0 of, let's think of a trickier one. Let's say x squared. One. Okay, give me 1 second. Hard to create limits. Some out of randomness. Okay, I don't like it. Scratching a little bit. Let's see this one. Okay, this one looks better, I think. Okay, let's evaluate this limit. Well, when x goes to infinity, where does x squared go? If x is big, x squared is even bigger. So this goes to infinity. Now, let's evaluate this one. 1 just goes to 1. X squared goes to infinity. X to the third goes even more to infinity. So then here you have 1 over infinity. What does this go to? Again, you will memorize. It's not going to memorize. You're going to understand. Like you're not even going to think about it with a little bit of practice. This goes to 0. Okay. So right now I just have 0 over infinity, which is just going to be 0. Okay. Like the whole idea of math in general is to start with simple rules and then just keep applying them until you solve the more complex problem. So, you know, I start with these pathetic simple rules, and by using them, I managed to solve this one. Okay, and now I can give even more complicated examples where we're gonna just use those. But again, the only ones I would recommend basically just understanding it, just because it makes evaluation everything so much faster, is the fact that constants just vanish over infinity and constants just explode under 0. If you know these two and you understand these two, you can basically evaluate any integral in like seconds. Okay, you just need to understand them really, really well. You can create all the limits from here. Now, I will write L'Hopital again because I think there was not enough emphasis on the most important / the hardest part not to mess up. I've said it in the lecture really fast, but I really want to spend 1 second on this. Hopefully, we have time to do we have time. Okay. L'Hopital. Some other cool thing here that now after you've done the seminar, the seminar or workshop or whatever it's called, is that you can use the fact that exponential is much, much bigger than power functions. And this you can use in an exam. Yeah, sorry about that, yeah. Exponential is much, much bigger than power functions. For those of you that have not done the workshop, you're gonna need to prove it first. Do not write on the workshop, I just learned that exponential is bigger than power functions, because you first need to prove it. For those of you that have already proved it, you can use it, okay? Now, the L'Hopital. The whole idea of L'Hopital is, I'll write in caps lock, only usable infinity over infinity plus minus and 0 over 0. Again, I could write bigger, but I think you got the point. Only use it in these cases. Just check 10 times before you apply it. Because in the exam, if you apply it wrong, you lost everything. You're not getting any partial credit because there's nothing to give there. Okay? And now everyone knows the whole idea of the L'Hopital thing, which is that, you know, if you have x going to some limit and then you have f of x, g of x. If the cases apply, is equal to limit x infinity, f prime of x, g prime of x. Okay? The idea is that these two cases, or 4 plus 1, if you consider minus infinity over plus infinity different, are the only undetermined cases. Everything else, every combination you can determine. 0 over infinity, it's just a constant over infinity. Like any other combination of these, I'll just write it like it makes sense. Because what are the alternatives? The alternatives are 0 over infinity, infinity over 0, etc., etc. And these you can evaluate. You don't need to apply a L'Hopital to it. What's 0 over infinity? You just have nothing and you divide it into a lot of things. So you get still nothing. Okay? And then infinity, you have an infinite amount of things and you don't even split it. Whatever. So you get infinity, even more things. So the idea is that you only use in indeterminate cases. These are called indeterminate, I think I made a typo, but it doesn't matter. Cases. In undetermined cases. What is that? It's undetermined cases. My English is getting bad. Okay, so it's undetermined cases. These are the only undetermined cases. Everything else you don't need to apply L'Hopital to it. And moreover, it's wrong to apply. In some things you can do it if you want. It's going to be more work, but you can do it. In every other case like this, it's wrong. It's a huge mistake. The limit is different. For those of you that have done the workshop, hopefully you've seen that you've applied L'Hopital and you got the wrong answer. So I can't emphasize this enough. Always check your cases. Now, interesting question. What does infinity minus infinity equal to? I have an even better one. What does infinity times 0 equal to? These are cases which you've seen. You've seen up to this point limit, so hopefully you're going to see. What are these cases equal to? That's a great answer. It's undetermined. These cases, you don't know. Infinity minus infinity is not equal to infinity or 0 or whatever you're going to think of. In reality, infinity minus infinity can be equal to any number you want, depending on the function. Same for infinity times 0. So how do you deal with these cases? Since they're undetermined, right? Keep in mind, I said that L'Hopital is only used in the undetermined cases, and it's enough because everything else can be computed. Did I lie? Did I lie when I told you that everything else can be computed here? No, not really. Let's take an example. Now, hopefully you're going to understand why the writing that he uses and the trick that he shows you makes sense. Let's take limits of x infinity, f of x minus g of x, okay? This is a thing, and I evaluated them, and I saw that this goes to infinity and this goes to infinity. Fair? So I'm stuck. I'm like, okay, the only theorem I know applies to fractions. What am I going to do here? I'm stuck. I'm panicking. Okay? And what you're supposed to do here is the trick that he's showed you, or you've probably seen by now, is you just factor out one of them. F of x, you just put it in front, and you get 1 minus g of x, f of x. Okay? Why did I do that? Because I can evaluate this thing. I can see what that's equal to. Makes sense? Makes sense. The only thing you got to keep in mind, the only thing I know about these undetermined cases is L'Hopital. So it means I have to make it somehow to use L'Hopital. Okay, I don't know how, but I just got to make it work somehow. Then the same applies for, let's say, limit of x goes to infinity of f of x times g of x the undetermined case. Again, I said this goes to infinity and this goes to 0. And I said, in this case, I don't know, we can put it like case 1, case 2, however you want to put the notes. I'm just showing you and talking at the same time. If you have this case, again, I told you, this does not equal 0, does not equal infinity. It can be any number you want in this world. So any number you give me is wrong. So the idea to do this one is, again, the trick that he's probably showing you is limit x goes to infinity, f of x, 1 g of x. Does it make sense why these two are equal, first of all? Why g of x is equal to 1 over g of x? There is just arithmetics. If you're not convinced, just give it a second, give it like 5 seconds with a piece of paper. And if you don't get it, just ask me, okay? But this is the standard way of writing it. And now you get limit x goes to infinity, f of x, f of x, 1 over gx. Okay? So I created my fraction, and now you're gonna say, okay, smartass, but this looks even uglier than before. How is this helping us? And now you evaluate it again. Remember, I said f of x goes to infinity. G of x goes to 0. So this thing goes to infinity. So now I just created an infinity over an infinity case, and I can just slam L'Hopital into it and take a derivative and solve the problem. Does it make sense what I'm saying? The same applies here. The same applied up top. I forgot to say it. When x goes to infinity, you know, I have infinity minus infinity case. I have no idea what that is equal to. So I just take a factor out, and I get this infinity here, which I don't know. Well, I don't know what it's multiplied with, but I evaluate this thing, and I see what it gives me. Again, this is infinity over infinity case. So I can apply L'Hopital again. I slammed the L'Hopital, I finished the problem. All right, it's just the trick here. Remember how I think I said in class that the trick in the by parts or the substitution is choosing that u and v, basically choosing what to substitute or how to spread your derivatives. The only trick you have to deal in limits or when dealing with limits is creating your fraction. Once you create your fraction and it's an indeterminate case, you slam L'Hopital into it. Everything's going to work out eventually. Okay, that is 100% going to give you the solution. Yes. Can I ask what example you're thinking of? When it diverges. Is that what you mean when it diverges?
I don't know, like sometimes the solution is just doesn't make it happen.
So it might be a phrasing typo because usually when the limit is plus infinity, it's another way of saying the limit does not exist. Because as I said, it just gets as big as you want. It doesn't go to like a number 500. So maybe that's another type of writing. That's one thing that I can think of that, you know, when it goes to infinity or minus infinity, just say it doesn't exist because it doesn't have a value. The other thing is just some absurd cases, which I can give examples of, but I don't think he would ever ask you to compute that. I think he even gave it in class. It's this weird ass function that goes like this. So do you know the sinus function? Okay, I'll show it to you afterwards if you want. Because if you don't know the sinus function, whatever, it gets more complicated than it needs to be. So we're just going to show it as an example. But again, I don't think you're going to have a case where the limit does not exist. The only case that applies to you that I'm thinking of is when it's plus infinity or minus infinity, and it's just a way of the people saying it doesn't exist, right? It just goes to any number you want in this world. So that's why it doesn't exist. But yeah, I'll explain it afterwards. I'll give you an example where it truly doesn't exist, but I don't think they would ask you to solve a problem where it doesn't exist. Anyway, now let's do the problem on this exam, on this beautiful exam. This is an exam from 2 years ago or something. Let's do this limit. Hopefully I can solve it. I don't really remember how, and I didn't have time to practice it, but I guess it's better for you guys because you see what I'm doing. So I hope nobody's gonna accuse me that I'm doing something too easy because this one is already longer than I can imagine. Okay, cool. This is my thing. I have to show limit when x goes to minus infinity of g of x. And then I have to show limit when x goes to infinity of g of x. We'll get to the last one if we have time. I think it's great practice. Okay, so this is what I need to do. And first of all, you tell yourself not to panic because this looks absolutely horrible. And then you just start writing some stuff, see if you can make sense of what's here. So, first step, you always do a limit. You evaluate it. Maybe it's easier than you thought. Maybe this whole formula is just here to trick us. I don't know. You can hope at least. So let's see. Okay, horrible. So this goes to infinity. This thing goes to minus infinity. This thing, x squared goes to infinity, log of infinity is still infinity. This goes to infinity. This thing, this thing goes to infinity. And now this thing, R is positive. I think it says that R is positive, right? Yeah, R is positive. Sorry. R is positive. Okay. So this E thing is E to minus minus. So it's E to the plus infinity, which is hugely infinity. So just to recap, okay? So recap where we are. We have minus infinity over infinity times infinity minus infinity over infinity. We're in a great spot. I have no idea what to do. Yeah, I don't know. We're gonna think of something. Again, I could at this point create some stuff and make some arguments based on what I know, but I'm gonna pretend like I don't know this. So what am I gonna do? I told you guys, we have this indeterminate multiple cases ugly thing. I'm just gonna bring it to the same denominator, slap a L'Hopital into it, see where I get. I don't know. Am I gonna get something? Maybe. It's better than where I am at least. So let's write this nicely. Limit x goes to minus infinity of 4x1 plus x squared, this log of e plus rx squared minus 1 plus x squared e to the rx. Okay. This doesn't look bad at all. Now, bring it to the same denominator. I don't know. I have no ideas. I'm stuck. So I bring it to the same denominator and I get 4x log of e plus rx squared times e rx plus 1, it's minus here, minus 1 plus x squared, 1 plus x squared, 1 plus x squared ERX. Okay. Honestly, I was expecting this to look much nicer, but apparently it's not really helping. Okay. Let's attempt to evaluate it now. Attempt, remember, the key word is attempting. So I have, it's always good to evaluate, like always. This is minus infinity. This thing is log of, this is infinity. This is log of infinity, so it's infinity. This thing is infinity. Now this thing is 0. Not bad, not bad. This thing is 0. This thing is infinity, and this thing is again infinity. Okay, so now I have this ugly, ugly thing. I have a lot of infinities, a lot of zeros. What do we know about infinity times zero? What do we know about everything else times infinity times infinity? Basically, you don't know anything here. Okay, there's nothing. And at this point, most of you just panic and be like, okay, this is undoable. Now you just split your limit into stuff that you can do. Okay, so I can't evaluate this whole thing all at a time. I have no idea. But maybe I can evaluate this part over here. That's infinity times zero. I'll just start with that. Let's try to evaluate that, see where it goes. So I'm going to evaluate limit when x goes to minus infinity of 1 plus x squared e rx. So everyone follow my logic. So I brought everything to the same denominator, hoping I could just apply L'Hopital and be done with it. Apparently the problem was a little bit more complex than that. The problem said, fuck you can't do that. Okay, it's not going to work out. Because you have, and again, I don't think I need to emphasize how bad it is. I have minus infinity times zero, infinity times zero everywhere. It's like a complete mess here. All right. So at this point, the first step that you need to complete for an integral is to evaluate for a limit is evaluate the terms. If you can't evaluate them, you can't do anything. So right now, I'm just getting the smallest part that I can compute and evaluating it. Okay, I'm just evaluating the smallest part. This is the smallest part. I'm just evaluating it. Now, let's evaluate this. This is just equal. Remember the trick I told you? I said this is infinity. This is zero. The trick I said was, hey, why not just write it 1 plus x squared, 1 over 1 e rx. But remember, I think I said that on the previous page. Okay, that's not bad, I guess. So this is limit when x goes to infinity to minus infinity, so for that, 1 plus x squared e minus rx. Everyone follow on that? I'm just evaluating this right now. Let's see. Where does everything go? This goes to infinity. This goes to infinity as well, because it's minus infinity there. Okay? So now when you learn the exponential thing, you would automatically say, okay, this is just zero. From the exponential bigger than power function. For those of you that have not done the seminar, you're in infinity over infinity case. You just apply L'Hopital. Okay? And you're gonna still get zero, I hope. Now, I was asked in the exam, you don't need to show me like the way I'm writing it here, basically just putting like a circle around it or an arrow showing you where everything goes. Like, this goes to minus infinity, this goes to infinity. This is enough for the L'Hopital. Like if you write this symbol of infinity over infinity or minus infinity over etc., that's enough for me. I don't need to have this whole justification, write 5 lines telling me that L'Hopital only applies to this and only works if the case is infinity over infinity. I don't need that. I just need for you to show me that you thought of it, you considered it, you checked it, and then you applied L'Hopital. Okay? So this small sign just showing me that it's infinity over infinity is more than enough for me. Okay? Just write it simple. Now, this is 0. This thing is 0. So this whole thing is 0. And now, I'm here again. So I have this one evaluated, which is fine. That's check. Now, this is infinity times infinity. This just gives me infinity, so I don't need to work here. This is infinity clearly. I just need to see what this is. What is this? And you probably guessed it by now. I'm just going to take it out and get the limit of that. So this was an exam problem, right? So this is this is in like 2-3 months from now on. But I'm just trying to show you that even the most complicated problems just require you to be calm and stick to the basics, stick with what you know and build from it. Okay? Again, from that, like it might look really weird for you guys, but I'm literally one line away from solving this problem. And you're not gonna believe it. So I said that I computed this, and now I have to do this one, the last part. And I have limit when x goes to minus infinity, 4x, this log ugly thing, x squared, e rx. Okay, I'm gonna use the exact same trick. Literally the exact one. I'm gonna get limit x goes to minus infinity, 4x ln e plus rx squared e to the minus rx. Okay, okay, I'll write one more step. The idea is that I'm writing this thing as 1 over 1 erx. So this is 1 over erx, which is just equal to limit minus infinity. So I just write it minus rx. Okay, and now again, I'm here, I evaluate, see what I get. When this goes to minus infinity, this goes to plus infinity. E to the plus infinity just gives me infinity. This goes to minus infinity. And this thing just goes, x squared infinity, log of this infinity. So again, this is enough for me. Minus infinity, infinity, slam the L'Hopital into it, apply it how many times you need, you're gonna eventually get, again, 0. One thing that you can tell me, again, for those of you that have solved it, which everyone would have solved this week's workshop by the exam, so you can use this in an exam, no stress about it. You can just say 0 because exponential, bigger power function. Everyone I've talked to about this, I've emphasized how strong this property is. Like, look at this. I just solved these two ugly limits instantly because I know exponential is much bigger than everything else. Okay? Now, so does anyone understand wait, like, I just took, okay, let's wrap it up and then we'll go over it and I'll explain it again, everything. Just to show you that the most complicated problems just work out if you just take your time and do it calmly. So let's re-put everything that we did. Limit x goes to minus infinity of 1 plus x squared erx. This was the ugly thing I needed to evaluate, and I was stuck and I had no idea and I was panicking and etc. Okay, this was it. I just copied it. Now, after my 2 computation or whatever, after I just took the time to evaluate everything, what did I get? I get this goes to 0. Okay? I just showed it here. That goes to 0. This thing goes to 0. Just showed it there. This thing, when x goes to minus infinity, x squared goes to infinity. So this goes to infinity. So what's my case? Minus infinity over 0. Do I need to apply L'Hopital for this? No, I don't even need to do that. This is just minus infinity. Okay, so now, what did I want to show you with this problem? I wanted to show you that these simple techniques that I'm talking about, that everyone is just laughing off, like, come on, everyone's going to do that. They're just, if you just take them step by step slowly and try them all, you're going to get the solution. So I started with this extremely ugly limit, which I was looking at it And I was like, and it looks something like this. Realistically, you can't find a limit that looks worse than this, to be honest. It's just, yeah, it's just infinities, a lot of infinities here, you get stuck. And then you say, I only know the L'Hopital theorem, so I need to create a fraction. That's the only thing I'm searching. I need to create a fraction so I can start evaluating, taking derivatives. So from here, I just created the fraction. I brought the same denominator here, brought the same denominator, and I got something even uglier. Okay? Let's agree this is much, much uglier. And now I evaluate it. It just, there's nothing else I can do. Okay? I want to apply L'Hopital. In order to apply L'Hopital, I need to evaluate my limit. So I evaluate my limit. And I realized I have an infinity over 0 here. Here I have a minus infinity 0, so even worse. And here I just have infinity. So, and this is the mistake. Like, you don't realize how important it is, but if you don't evaluate this integral and are automatically in the mindset of I need to take a derivative right now, this is L'Hopital, clearly that's what I know, then imagine you would have needed to take a derivative of this thing. And it would have been wrong. You would have spent like half an hour on this at least. So a lot of mistakes. Do you guys understand? Like if you here just said, oh, we have on the same line, on the same thing, it looks absolutely ugly. It has to be L'Hopital. I'm just going to apply L'Hopital. It's going to work out. Wrong. On multiple things, you need to evaluate it first. So I needed to evaluate it first. I'm not smart. I just know the basics. In order to apply L'Hopital, I need to be in an infinity or infinity case. So I need to evaluate this. Okay? I evaluated this. I start with the denominator. The denominator is an infinity over 0. So I don't know what it is. At that point, I just use the trick, which is this ERX is just 1 over 1 ERX. Okay? I create my fraction. Again, as you can see, all the steps are repetitive. I evaluate, create my fraction. Evaluate, create my fraction. Okay, everything is repetitive. So I evaluate this. It's infinity over 0. I know this is undetermined case. I create my fraction. I get to this fraction, which is infinity over infinity case. And I can apply L'Hopital. If you apply L'Hopital to this, you're gonna get something, you're gonna get 0 in no time. If you if you don't remember that exponential is greater than power function, apply L'Hopital, gonna work out in seconds. If you remember exponential is greater than any power function, this is automatically 0. Okay? Since we have do we have 2 minutes left? Since we have 2 minutes left, I'll actually show you how I would apply L'Hopital to this. Okay, let's say I didn't remember. Let's say I was stressed. I don't remember that exponential is bigger than power function. Let's just apply L'Hopital to this. This is equal to limit x goes to minus infinity. What's the derivative of this? 2x. What is the derivative of this? Minus r e minus rx. Okay? Now, what do you do with this? What does this go to? I have no idea. So, first of all, does everyone follow the derivatives? Does everyone understand how I apply L'Hopital to this? Okay. So, what do I do now? I mean, I have no idea. Let's evaluate it again. X goes to minus infinity. This goes to minus infinity. This is e to the infinity, so with a minus in front, this goes again to minus infinity. This is again, infinity, infinity, I can apply L'Hopital. No stress. Everything is like, the derivatives are easy, so why would I stress about it? I just get 2 minus r squared, e minus rx. Now, what do I do now? Evaluate it again. What is 2 when x goes to minus infinity? Just 2. What is e to the minus rx? Infinity. So I got 2 over infinity, that's just 0. Okay? Cool. So I evaluated this and it's equal to 0. Now, this is infinity, so I just have to evaluate this ugly, ugly, ugly thing here. Evaluate it again. I just take it out of the limit, and I evaluate it here. Again, same exact trick. I can't emphasize how strong this trick is. You only know how to deal with fractions. This trick creates your fraction. Hence, I think you should memorize it. So now you have this limit, whatever is here ugly, over this ERX. And again, you are in a minus infinity over infinity case. You can apply L'Hopital happily here, and you're going to get an answer. Similar, this thing is just going to go away, and you're going to get a constant over infinity, still 0. Okay? Or again, you remember that exponential stronger than power function. I can't emphasize how impactful that is. Okay, so I evaluated this is 0. Now I go back in my thing. And at this point, although you've already done a lot of work, you should be ready like, okay, now that I evaluated, I have a fraction in which I know everything. So I can either apply L'Hopital to it, or I'm going to get the answer. Those are the only two cases. Literally the only two cases. So at this point, I look and I get this thing underneath is 0. As I evaluated it, this thing above is 0, and this is minus infinity. So I get minus infinity over 0, minus infinity. And yeah, that's right. And yeah, that's kind of it. Like, just keep in mind that however ugly the limit looks, and let's agree on something. This was an ugly limit. It wasn't a nice one, okay? There was nothing nice about it to start with. And we just split it, we evaluated. So I know, first rule, just evaluate your thing. Evaluate, and then create fractions, and then evaluate. And the last one is actually applying L'Hopital, if the case. Okay, I'll put another evaluate there somewhere, but I don't know where. Like, evaluate as much as you need to. At every step, you should know where the limit is going and why you are doing what you're doing. Like, as you see, everything that I did had a purpose. I evaluated the start to see if I can just put the number. Then I created my fraction, and I evaluated the fraction, see if I can apply L'Hopital or not. And then, while evaluating the function, I just had to evaluate these two ugly terms. Term 1, term 2. And yeah, that's kind of it. The problem just solved itself, literally. It's not much. I think the hardest part here is to keep calm when you see this thing, and you're like, I got to evaluate that. That looks kind of nasty. Okay, I think that's the hardest part, to just keep your calm. It has to be solvable using the methods you know, and you haven't learned any amazing, cool things. You've just learned L'Hopital and basically transform into fraction stuff. So it has to work that way. But I think that's kind of it. So we ran out of time. But yeah, I showed you the assignment at the start of class. It's hopefully going to be posted. So yeah, let me know how it works.